Good evening. We're group four. Christopher Lee, Sarab Agarwal, Robert Martin, Taylor TG, and myself, Michael Cruz, will be presenting BLIP, Bootstrapping Language Image Pretraining for Unified Vision Language Understanding and Generation. So what was the motivation behind the BLIP model architecture? Previous VLP models had many obstacles to overcome. One of the most imperative was how to obtain large volumes of image text pairs. One solution was using images accompanied by human annotated captions. However, this was very time and labor intensive and wasn't optimal to scale up BLP models. Another option was to gather image text pairs on the internet via web scraping or other techniques, but this introduced noisy textual data into the model because captions don't necessarily accurately represent the image they're describing. So this method also requires a lot of human intervention to remove noise from the data set. To solve this problem, the BLIP model introduces a novel cap filter module, which is a mechanism that generates synthetic captions, as well as filters both captions obtained from the internet and the synthetic captions to reduce noise in a data set. The second problem lies in the inherent task-specific nature of the transformer model, of the transformer architecture. In general, encoder-based transformers are used for classification and understanding-based tasks, whereas on the other hand, decoder-based transformers excel in generative-related tasks. To create a unified VLP model with the capabilities of both understanding and generation, the BLIP model introduces a multimodal mixture of encoder-decoder model, also known as an MED model. Now, the MED model has four components: a transformer encoder for visual data, two transformer encoders for textual data, and a transformer decoder also for the textual data. Because the image encoder is so computationally intensive, each image is processed through a transformer one time for each forward pass, and in contrast, each text sample is processed 3 times, once through each textual transformer. Now, the first component of the MED model is the vision transformer, which uses the same architecture from the paper and images worth 16 by 16 words. During training, each image is resized to a resolution of 224 by 224, and then during fine-tuning, they're resized to 384 by 384. Now, during the forward pass, each image is divided into 16 by 16 patches, and then each one of those patches are flattened and stacked on top of each other, and then an extra class token is pre-appended to the sample, which represents the global image feature. Then positional encodings are added to each patch, and the embedding features are passed to the self-attention layer, as you can see here. In this layer, using key, query, and value matrices, the self-attention scores for the samples are computed. The attention scores are then added back to the original embedding with this skip connection and then normalized across the layer. The normalized attention scores are then passed through a feed-forward layer and then again are added back with the original attention scores and normalized across the layer. The output of the vision transformer is linearly projected and will be used for all the other components in the MED model. The next component of the model is the textual transformer. This encoder uses the pre-trained BERT-based model to encode the text samples. For each forward pass, the tokens are embedded, and like the vision transformer, a class token is pre-appended to the sequence. This token represents the summarization of the sentence. Both the vision and text encoder share similar components, but notice how the self-attention layer is used in the vision transformer is changed with the bidirectional self-attention layer in the text encoder. In bidirectional self-attention, 15% of tokens in a sequence are masked. Of this 15%, 80% of the tokens are substituted with the masked token, 10% of the tokens are exchanged with a random token, and then 10% of the tokens remain unchanged. By taking this information from both the right and left sides of the token's context, bidirectional self-attention generates improved token embeddings as well as an improved feature representation for each text sample. The output of this text encoder is linearly projected to the vector of the same dimensionality of the vision transformer output. Now, these two outputs, during the backward pass, the image text contrast of loss is computed. This is computed between the vision and text encoder outputs to align each modality's feature representation in a global feature space. The objective of contrastive pre-training is to jointly train an image and text encoder such that the cosine similarity of the correct image text pair is maximized. At the same time, the cosine similarity of the dissimilar image text pairs should be minimized. This is accomplished by stacking all images in a batch on top of each other, creating a matrix, which is similarly done to the text samples. By multiplying the image matrix by the transpose of the text matrix, a global feature space is computed where the diagonal of said matrix should represent the intersection of each correct image text pair. The cosine similarities in this diagonal should be maximized, and the off-diagonal elements should have their similarities minimized. The next component is the image ground text encoder. This transformer will later be used during fine-tuning as the filtering mechanism in the cap filter module, which will be discussed later in depth. Like the previous text encoder, each word token is embedded and a learnable task-specific token is pre-appended to the sequence. The token will be used as the output of the encoder to represent the multimodal representation of the text modality and the image modality. Again, this transformer has many of the same layers as the previous encoders, but notice the addition of the cross-attention layer. This layer takes the final query key matrices generated from the vision transformer and calculates self-attention scores using the value matrix of the image ground text encoder. This mechanism essentially injects visual information into the attention scores of the image. The learnable task-specific token is taken from the output and is used to calculate image text match loss. Now, the image text match loss is a binary classification task. During the learning stage, the model uses the pre-appended token as the transformer head, right, as you can see here, to predict whether each image text pair is a positive, meaning the pair is a match, or a negative, meaning the pair is not a match, given the multimodal feature representation along with human annotated labels. As an optimization strategy, the model employs a hard negative mining strategy where the model identifies samples it got wrong from the ITC loss, and it reintroduces those negatives into the samples. This enables the model to distinguish between positive and negative examples better. During fine-tuning, this encoder will be used to find positive or matching image text pairs and filter out negative image text pairs for both web caption and synthetic caption captions. The final element of the MED model is the image ground text decoder. This will be used as the autoregressive synthetic captioner in the cap filter module. Like the image ground encoder, the textual tokens are embedded, and a decode and EOS token are pre-appended to the sequence to represent the beginning of a sequence and the end of a sentence tokens, respectively. The image ground encoder and decoder share all the same model parameters, including the embedding layer, the cross-attention layer, and the feed-forward layer. This method was employed because all of these layers are not specific for a particular task, and it improved the computational and storage efficiency of the model. However, unlike the encoder, the image ground decoder replaces bidirectional self-attention with a causal self-attention mask. This masking technique confines transformer queries to the preceding key value pair positions, as well as the current key positions. All tokens that are in positions past the current token are masked with negative infinity, allowing the model to build feature representations for these masked keys. This allows for autoregressive learning. The causal self-attention layer and the bidirectional self-attention layer are not shared parameters because they're task-specific. Bidirectional self-attention builds feature representations for the current token, while causal self-attention builds feature representations for future tokens, which is better used in autoregressive downstream tasks such as synthetic captioning. The output of the image ground encoder is used as the language modeling loss. During learning, the language modeling loss calculates the next token in a sequence using softmax along with cross entropy, given an image and the previous tokens in the sequence. To decrease the certainty of the prediction, 0.1% is distributed from the token predicted to be the next token in the sequence to all of the tokens. During fine-tuning, the transformer is used to generate captions given an image. These synthetic captions actually turn out to be more accurate than image text pairs obtained from the internet. And next, we'll go on more in depth to talk about the novel caption filtering mechanism.
The cap filter system. The cap filter system's main goal is to improve both the quality and quantity of the data set. It does this by filtering out noisy data and providing higher quality synthetic captions. An example of how this would work is here. You can see this picture of a chocolate cake. The web caption for this picture is Blue Sky Bakery in Sunset Park. This data, the caption doesn't provide any usable data for the model. This is the kind of caption we consider noisy and we would want to have filtered out by the filtering system. The captioning system would then provide a caption that's more descriptive, like chocolate cake with cream frosting and chocolate sprinkles on top, which is the kind of data we want to have. So we're going to look at how this would work. So you'd start by pre-training your MED on your full data set. The data set would be image text pairs from the web, as well as image text pairs from human annotated data sets. With your pre-trained MED, you can then start the dataset bootstrapping. You start this by fine-tuning the filter, which runs on the image-grounded text encoder. You fine-tune it using the human annotated data on the ITC and ITM loss functions. Once you have your fine-tuned filter, you then run your unfiltered web data, your image text pairs, through the filter. This would then give you a filtered set of image text pairs that you can then use. You then fine-tune your captioner, which runs on the image-grounded text decoder. The captioner then takes the images, just the images, and provides synthetic captions for them. But these captions aren't always perfect, so they have to also be sent through the filter. Once you've filtered all those, you then have a full set of image text pairs from the web, as well as image text pairs from synthetic captioning. You can end up with anywhere between 1 and 2 captions for any image, which is how it increases both the quality and quantity of the data set. You then recombine this with your human annotated data, send it back to the beginning, where you train a new MED. You can then either start this process again for theoretically improved data sets, or you can then send your new model down to downstream tasks. So some examples of how this ends up working out. You can see here for this image, the web-based caption, again, is a noisy caption that we don't want. It has context about where the image is, but nothing about what's actually in it. Synthetic caption then describes what's in the image. You can see a couple more examples here where it's very similar. There's context about where the image is, but nothing about what's actually in it. And synthetic caption then tells you what's in it. But the synthetic captions aren't perfect either. Sometimes the web data is better than the synthetic ones, and that's why they also have to be filtered. And now a brief discussion about the data sets used in this. The models were pre-trained on 2 different sort of sets of data. The first set of examples was run using 3 web-based data sets totaling 14 million image text pairs, as well as 2 human annotated data sets with 450,000. An additional set of experiments were then run with the addition of a noisier web-based data set with 115 million image text pairs. The fine-tuning was done using Cocoa, and a lot of the experiments were run, the evaluation had their own data sets, and the results will then be done by Robert.
So before going into the different experiments that were conducted in this paper, we're going to first explore some of the different metrics that were used for evaluating performance. The first metric is recall at K, where K can be any value over 1. So recall at 1, 5, 10, so on. This represents like the number of recommended relevant items among the top K divided by the number of relevant items that are in the system or query. So in the case of BLIP, you can think of if you have an image and you generate 10 captions for it, recall at 1 would be the recall score for the top item, recall at 5 would be for the top 5, and so on. The second one we'll be going over is mean rank. So Q here denotes query. So think of in the case of BLIP, you have all these different images you're generating, and you are getting this value right here. This is the rank I value. So for each of these queries, you are getting the rank of the first relevant item. You're summing all of those ranks together, and then you're finding the mean. The third metric we'll be going over is mean reciprocal rank, which is very similar to mean rank, except for instead of just using the rank I value, we use the reciprocal value. So the utility you get from this is that it punishes the score that gets generated the further away the first relevant item is from the top. So this is if you have your first relevant item is at rank 1, then you'll get a good score. It'll be 1 over 1. If it's at 500, you'll get 1 over 500. And this will affect the resulting mean reciprocal rank score. The fourth metric we'll go over is bilingual evaluation understudy, or BLUE. So the first part of BLUE is this BP, which represents a brevity penalty. This scales as the ratio between the length of the generated caption and reference captions differ. This brevity penalty is then used in conjunction with the sum here, where you basically calculate the precision of all of the n-grams, and you get the log of that value. You multiply that by this weight, which is uniform. It's 1 over n. You sum up all of these values from 1 to n. So if you think of like you have a caption and you're going to break it up into n equals 1, 2, 3, we're getting the different sets of nearby characters in the caption. And you're going to calculate, you're going to sum up all of those scores where you're going to get the precision, the log of that, multiply it by this weight, and you're going to sum all that up, and then you're going to put that over e. So this exponent here, so it's going to be e to this power that gets generated here from the sum, multiplied by the brevity penalty, and that's how you'll get blue. Then the fifth metric we'll cover is consensus-based image description evaluation, or CIDR. So the first part of CIDR that you need to calculate is CIDR n. You calculate this for all the n-gram pairs. So think of it as effectively the average cosine similarity between a candidate caption and a reference caption. You can see here you sum it up for all these gn of Sij. That represents the term frequency inverse document frequency weighting, which will not be covered in this, but I definitely recommend that you look into the paper more so you can get a more detailed explanation of this. This value is then multiplied with gn of ci. This represents a vector that corresponds to all the n-grams of length n for the candidate. Then you basically get all these CIDR n values, you multiply them by the same weight, 1 over n, and you get them for all values of n from 1 to n. So you can think of it as you have all these different CIDR n scores you're going to be calculating for each of the different captions, and then you're going to get the sum of all those together. This is why it's called consensus-based, because you're getting a CIDR n value for each of these different values of n for the n-gram calculations. This is kind of viewed generally as a sort of evolution of BLUE. And then finally, semantic propositional image caption evaluation, or SPICE. SPICE is a bit simpler than CIDR, at least with how it's calculated. First, you calculate the precision and recall. These precision and recall values basically represent the number of correctly predicted semantic propositions in the generated caption divided by the total number of semantic propositions in the generated caption. And then same thing down here on the top, at least, the number of correctly predicted semantic propositions in the generated caption is divided by the total number of semantic propositions in the reference caption. So using these precision and recall values, you can combine them together over here to get the FN score, or as it's noted, SPICE. And it's 2 times the precision value times the recall value over the precision plus the recall. The SPICE evaluates captions by using these values together. And how it gets these values is it makes these graphs from the captions as well as the reference captions and the generated captions. So you can think of it as, instead of looking at just the raw text, you're going to be generating these graphs that are supposed to represent each of these each of the captions. So it's kind of the same thing as where 2 people can come to the same conclusion, but they took different steps to get there. So since we covered those metrics, we'll move on to some of the experiments. This is the first experiment we're going to be covering, which is image text retrieval. All of these methods have been fine-tuned. You can see here the method name, and then you can see in this column the number of pre-trained images that were used. On the COCO dataset for text retrieval, you can see that BLIP performed the best. With recall at 5 and 10, BLIP with caption filtering performed the best. You can see for image retrieval, once again, the BLIP performed the best. BLIP with 129 million pre-trained images, and then BLIP with caption and filtering. For Flickr, you can see for text retrieval, BLIP once again performed the best across the board. And for image retrieval, you can see the same sort of story. For image text retrieval, but with 0 shot, you can see on text retrieval, BLIP once again does the best. And for image retrieval, once again, scores the highest recall values. This is very great, especially when you're considering the number of pre-trained images. As you can see here, Align used 1.8 billion images, as where BLIP used 14 million and 129 million respectively, including on the BLIP with the different backbone, the VITL, where it even scored a better set of score. It got it achieved even better evaluation metric scores. If we move on to this study, which is for image captioning with fine-tuned methods, here you can see the method, and here you can see the number of pre-trained images. This is on the no-caps validation dataset, which is pretty interesting because instead of just looking at the overall performance, you can actually also look at individual subsets of the data set and see how the performance was. These are in domain, near domain, out domain, and overall. So the individual domains, if you think of it as like a data set that has planes, in domain would be an image with a plane, near domain would be an image with a car because it's a vehicle, but not a plane, and out domain would be an image that has none of the classes in it. Overall, it's just the entirety of the data set. So you can see in domain with C and S denoting CIDR and SPICE respectively. You can see BLIP with captioning and filtering performed the best. In domain, in near domain, and also in out domain, as well as overall. On the COCA caption Kapathy split, however, you can see that Lemon actually got a better blue score, and it tied with respect to CIDR scores. This is explained by the authors to be potentially due to the increased number of pre-trained images for Lemon. So theoretically, if there were more pre-trained images for BLIP to be trained on, the authors expect that there could be better performance on BLIP with the typical VIT-based backbone with captioning and filtering. So of the tasks that the paper covered, some of them required the architecture to be altered slightly. There were 3 of those. This is the first one. This is visual question answering. So the goal of visual question answering is to predict an answer given an image and a question. To set this up, they had to rearrange the pre-trained model. Image question pair was encoded into multimodal embeddings, as you can see over here. These embeddings were then passed to an answer decoder, and then the resulting VQA model is tuned using LM loss, which was mentioned previously. By doing the alteration, you're then able to do visual question answering, and these are the results. Here you can see the method, as well as the number of pre-trained images. And here you can see the VQA results where BLIP with captioning and filtering performed the best. The second task that required alterations to be made to the structure is natural language visual reasoning task. So the goal of this task is to predict if a sentence describes an image pair. So once again, they need to do some setup. They need to rearrange the pre-trained model. They need to pass both of the images into image encoders that are set up with the same weights at the start. Then all the embeddings are sent to 2 cross-attention layers, and the resulting outputs are merged together, and then they're fed to each block's respective feed-forward network. By making this alteration, now they can pass in 2 images, and they can ask, or they can specify 2 planes that are both in an airport, for instance, and each image it has like 2 different planes in an airport, and they can get a true or false answer. So with respect to their performance on this task, you can see that BLIP once again performed better. However, BLIP with captioning and filtering did not. The authors theorized that this was potentially due to a domain gap occurring since the web data has been transformed to caption and filtering. So you can think of if you have the same data set and you have 2 images of planes and their captions are kind of similarly labeled. Once you pass those into a caption, pass those through captioning and filtering, you might actually get captions that are pretty different. And they might be more accurate to what a human would say, but now they have diverged more. So that's why you can see here that BLIP with 14 million pre-trained images and BLIP with 129 million pre-trained images actually perform better than BLIP with captioning and filtering. The third task where the architecture had to be altered was the visual dialogue task. So the goal of this is to predict an answer using a question-answer pair, dialogue history, and the image's caption. So to set this up, they also had to rearrange the pre-trained model. They concatenated image and caption embeddings from an image encoder and a caption encoder. Then they passed these embeddings to a dialogue encoder using cross-attention, where the dialogue encoder also takes in the dialogue history. Then they trained the dialogue encoder with IRM and loss. So if you've ever utilized something like ChatGPT, you know that it kind of takes into consideration previous things you've said try to think of that when you're thinking of visual dialogue task. It's taking into consideration not only the image, not only the question answer pair, but also the dialogue history, and it's giving you a true or false answer. So for the results on the visual dialogue task, you can see BLIP performed the best of the 3 methods that were tested. That includes with mean reciprocal rank, mean rank, and all of the recall values. Another task that was experimented with was the text to video retrieval task. This is showcasing some methods of zero shot as well as fine tuning. You can see that BLIP here performed the best of all these methods. And the final one that we'll be going over is the video question answering with zero shot and fine tuning. This one's kind of interesting because you can see that BLIP on the MSVD QA dataset actually performed very admirably, actually better than HME with fine tuning. But on the other dataset, it did not perform as well when compared to these methods that use fine tuning, but it definitely beat out VQAT, which is fairly, and the performance gap here is actually fairly distinct, I would say. Now, since those are individual experiments showcasing the performance versus other methods are complete, we'll go over showcasing how you can augment BLIP with data, augment how BLIP will perform data bootstrapping due to the captioning and filtering. So because of the structure of BLIP, you're actually able to kind of turn quite a few different knobs to try and get different levels of performance. Here you can see the pre-trained data set that was used. This showcases whether or not a caption or filter were present. So X denotes that it was not. If there's a check mark, it denotes there was. B and L correspond to the backbone that was used for the caption or the filter, B being a VIT-B, L being a VIT-L. So for retrieval with fine-tuning, you can see on text retrieval and image retrieval, the bigger the backbone or the larger the backbone for the immediate itself, as well as the increase and inclusion of the captioning and filtering seems to boost performance. And this sort of behavior is seen also with retrieval with zero shot, as well as caption with fine tuning and caption with zero shot. And you basically see as you include captioning and filtering, you can see performance gains, as well as when the size of those caption and filters, or rather the backbone that they're utilizing, increases as well. You can see the performance gains increase. In each of these individual sections as well, you can see that the highest scoring metrics are from the models that had captioning and filtering, ideally with larger backbones. There were 3 different ablation studies that we thought would be important to cover. The first one was for beam search versus Nucleus sampling. So these are 2 different ways to do synthetic caption generation. Nucleus sampling is like a stochastic decoding method, and you take each of the tokens that are sampled from a set of tokens, and whose cumulative probability exceeds a specific threshold. As where beam search is a deterministic decoding method, and it aims to find the most likely sequence of words given a probabilistic model. And you can see here with beam search, it actually has a lower noise ratio, but Nucleus sampling actually performed better in all metrics for retrieval with fine tuning, retrieval with zero shot, caption with fine tuning, and caption with zero shot. On all of these different data sets as well, you can see that Nucleus sampling performs better, even though it has technically a larger noise ratio. That's something that was not incredibly clear to me at the beginning of researching this paper, but as you go through it, you kind of realize that if you get rid of all noise, that's not necessarily a good thing, or rather, a decrease in noise does not necessarily mean that you'll get an improvement in the quality of information. This ablation study showcases the results of encoder and decoder parameter sharing and where it occurs in the architecture. You can see that the highest performing version of the model was when all except the self-attention were shared. So you can see here for retrieval with fine tuning on Coco, retrieval zero shot flicker, caption with fine tuning, and caption with zero shot, you can see that in all metrics, the highest performing one was the one that had all except self-attention. None, you can see, actually has a larger number of parameters and performs worse than all except with self-attention. And the final ablation study is for caption and filter parameter sharing, where you can see that when the parameters are shared, the noise ratio is decreased drastically, but similar to the first ablation study, when they're decoupled, the noise ratio is increased, but the performance as well is better. So this kind of showcases that you do not necessarily, a decrease in the noise ratio does not necessarily result in an increase in performance. And that's over, once again, retrieval fine-tuning, retrieval zero shot, caption fine-tuning, caption zero shot. So what are the limitations of BLIP? The first limitation is higher computational costs, especially if you're going to be doing full captioning and filtering, data bootstrapping for an entire new data set. This is kind of expected since this is introducing a new method of like augmenting a data set to actually utilize BLIP not only for the MED, but to actually do the caption alteration, actually come up with potentially higher quality captions. That's going to take a lot of computing power, especially if the data set is very large. Residual noise loading downstream models. You cannot get rid of all noise. And as you saw in some of the ablation studies, reducing noise does not necessarily mean in and of itself that you'll get better performing downstream models when they go to be used for various tasks. And finally, annotation limitations, at least not yet, or not currently, there's no way to have a perfect annotation or a perfect caption. That is something that's probably not news for many, but it is just something to take into consideration when you do get large performance gains from new methods like BLIP, to remember that it is not a magical solution that will make everything better. It is a tool like any other, and you need to consider the fact that usually there's no tool that just solves everything. So for conclusions and future work, the captioning and filtering improved the dataset quality and boosted downstream task performance. This was seen throughout all of the different experiments and the results that we showcased. You could see that even in situations where the performance was close or maybe didn't hit the mark, it was still performing incredibly well. And the MED is a versatile model, and it excels in visual language understanding generation. And it's worth noting, as a unified model, it's able to perform a plethora of different tasks. And you also saw that even with some slight alterations, it was able to perform various additional tasks, VQA, NLVR2, as well as visual dialogue. So for future work, exploring multiple bootstrapping rounds to refine captioning and filtering. In BLIP, they only do this once for concerns of computational costs, as well as the data sets that were already being used were fairly large. So potentially, if you would like to do this in the future, you would need a very large amount of computational power. Generate multiple captions per image for richer data. So instead of generating one new synthetic caption, maybe generating a set of them that could be used in conjunction to try and get a more optimal set of performance metrics. And finally, create a larger ensemble of models to boost captioning and filtering performance. The captioner and the filter, as showcased earlier in the presentation, are relatively simple in structure. So utilizing an ensemble of models could potentially boost the performance of those components. And these were the references used for the presentation. Thank you so much for watching the presentation. We hope that you look into not only this paper, but many of the supporting papers that the authors cited in theirs. We hope you have a good rest of your day, and thank you for watching.